With today's lesson, we begin Module 4, which is dealing with non-proportional relationships. And so our first part of our first lesson is 4.1a, representing linear relationships using tables. And our goal with this lesson is to use a table to show certain values of a relationship between two quantities in a real-world situation. Back in Module 3, the title of the lesson was Proportional Relationships, and obviously this module we're dealing with non-proportional relationships. Now, the types of relationships or equations that we were dealing with in Module 3, they were all still linear. If we graphed them, they would all form a straight line. In our equations for this module, they're still going to be linear. They're still going to be a straight line, but they're not going to be proportional like we had, not all going to be proportional like what we had back in Module 3. For example, back in Module 3, if we were given a table, we would be told to look for the constant of proportionality in order to determine if the table was if the table was proportional or not. And so what we would do is we would use k is equal to y over x. And we would determine that the table represented a proportional relationship by finding that the ratio for all the y values, so all these y values here, over their corresponding x values, all simplify to the same value. And so in this table, we would have 3 over 1, 6 over 2, 9 over 3, and 12 over 4. And so for all those values, we would get k is equal to 3 over 1, or just 3. Because we have that k value, because we have that constant of proportionality, we know that that table is proportional. In the same way, if we have a graph, we can determine a graph is proportional or not just by looking to see if it passes through the origin or not. Now with this specific example, we see right here that the graph does pass through the origin. It goes right through the origin here. Therefore, we know that this graph represents a proportional relationship. Okay? So again, from a table, we look for the k value. For a graph, we just look to see if it passes through the origin. Now, this is all back in Module 3. With Module 4, things are going to change. We're not going to have a constant of proportionality anymore, and we're not necessarily going to have graphs that always pass through the origin either. So getting back to Module 4, Lesson 1, dealing with the table, the key thing that we have to keep in mind is that with a table, the ratio of the y values over the x values will not be constant, but the rate of change will be constant. You guys need to go ahead and write that down. That's important for this lesson. And so for our first example, what I want to do is I want to show you an example of a table where it does not have a constant of proportionality, but it's still a linear relationship, meaning that it's going to have a constant rate of change. So for our first example, we have a table where we have x values of 1, 2, 3, and 4, and y values of 7, 9, 11, and 13. So what I want to do again is look at the constant of proportionality to determine that that is not a consistent value, but then I also want to look at the rate of change to make sure that that is a consistent value. So first of all, with our constant of proportionality, we remember using k is equal to y over x. And so we're going to go ahead. I want to take a look at this set of ordered pairs first. And so we have k is equal to 7 over 1. Well, that just simplifies to 7. Okay? Now, in order for this to be a proportional relationship, my constant of proportionality for all 4 of these ordered pairs must also equal 7. If they don't all equal 7, then it is not a proportional relationship. Again, meaning that the graph would not pass through the origin. So let's look at the next ordered pair right here, where we have 9 and 2. So we have k, again, is equal to y over x. And so again, this time we're using 9 and 2. So we have k is equal to 9 over 2. Well, if we simplify that down, that is equal to 4.5 or 4.5, however we want to write that. The key here is to recognize that this 4.5 value and this 7 value are not equal to each other. So therefore, we know that this table does not represent a proportional relationship. Okay? Now, with that being said, however, this table can still represent a linear relationship if it has a constant rate of change. So if we remember back also to lesson 3.2, from a table, we have m is equal to delta y over delta x. Okay? This formula here, different than what we have here. In this blue formula, we're just looking at the y values and the x values. With this green formula, we're looking how the x values and y values change. So if we look at the x values, we see that we're adding 1 each time. And for the y values, we're adding 2 each time. And so our bottom down here, that's going to be our delta y value. Up here is going to be our delta x value. And so we have m is equal to 2 over 1. Our rate of change for this problem is 2 over 1, even though this problem does not have a constant of proportionality. What this shows is that this table is linear. It would make a straight line if you graphed it. However, the graph would not pass through the origin. That's what we're trying to communicate here. The line does not pass through the origin, but it is a straight line. Okay? So that's our first non-proportional linear relationship. So again, all that to say is that if we were to graph this, it would make a straight line, but that straight line would not pass through the origin. It would cross the y-axis somewhere else. Alright, so for another example of this, we have another table. I set this table up going vertically instead of horizontally like the other one. Our x values are -4, -1, 2, and 5. Our y values are 7, 5, 3, and 1. Going back to our constant of proportionality again, k is equal to y over x. And what that means again, we're just taking our y value, placing it over our x value. We're doing it for all 4 of these ordered pairs. And if all 4 ratios are equal to each other, then it is a proportional relationship. If they're not all equal to each other, it's non-proportional. So let's take a look at what happens when we use these values. We get k is equal to our first order pair, -4, 7. So we have 7 over -4. And that's going to be like -1 1/3 or something like that. And 1 3/4. I was wrong on that. So 1 -3/4. Okay. If we do another set of ordered pairs, let's do the second set of ordered pairs right here. We have k is equal to 5 over -1. Well, 5 over -1. That gives us a k value of -5. So obviously this k value here, this k value here are not equal, telling us that we have a non-proportional relationship in this table. That again does not mean though that it's not a linear relationship. If we look at our x values, we're going up by 3 each time. Our y values on the other hand, we're going down by 2 each time. So therefore our slope, or our rate of change, measured by delta y over delta x, we're going to have m is equal to -2/3. Okay, so not a proportional relationship, but still a linear relationship because it does have a constant rate of change where m is equal to -2/3. Alright, so for our next type of example, what we're going to do is I'm just going to give you an equation, and we're going to use that equation to fill in a set of values on a table. So for this example, I'm giving you the equation y equals 3x minus 1. And so in this, what we want to do here is we want to come up with 4 x values that we're going to use in this top row here. And we'll use those as our input values, where we take these 4 values one at a time, substitute them in for x, solve the equation to get our output y, and then fill in those y values in the bottom of this table here. Now because this is just a made-up problem, we can use any x values that we want. I would encourage you use 0, because 0 is going to be the easiest x value to use. I would also encourage you to use at least one negative number, and then a couple positive numbers. Usually those are going to be our easiest values to work with. Now I don't want to overcomplicate things here, but I do want to help you with these problems that you might come across in the future. So in order to help you come up with x values that are easier to work with, I would encourage you to look at the denominator of our slope. In this case, the denominator is 1. Now since our denominator is 1, it is fair game to go ahead and increase your x values by 1. If your denominator is something other than 1, let's say 2 for example, then you would want to increase your x value by 2. And that will just make it easier as the problem goes along. And I'll show you what I mean by that in our next example. Getting back to this problem, however, again, a negative number, 0, and a couple positives. I would encourage you to keep the numbers small. So negative 1, 0, 1, and 2. Those are fine values to use if you're just given a generic equation where you're asked to fill in a table. Now what we have to do for these again is we need to take each of these x values one at a time, substitute them in for this, solve, and then write in the answer that we get for our y values. Now this process can seem tedious and time consuming, and I'll tell you now that in future lessons I'll show you a shortcut so that it's not going to take so long. But for now, this is the process we have to go through. So to start with, I'm going to rewrite the equation over on the right side of my paper. And what I'm going to do is I'm going to, again, substitute my x values in for x. So here's what that's going to look like. So what I did, I just took out the x variable and substituted in my first x value, which is negative 1. So I took this negative 1 here, substituted in for x. So now I'm going to go ahead and I'm going to show my work. So I have y is equal to 3 times negative 1 gives me negative 3. Negative 3 minus 1, and that gives me y equals negative 4. So my first y value is going to be negative 4. Now I have to repeat that same process for the other 3 x values in this table. So I would want you guys to show all 4 of these equations written out so that I can see your work on how you got every single y value on the bottom of this table. For the sake of space on my iPad, I'm just going to erase what I wrote already and fill in with the different x values. But again, I would expect to see 4 sets of work for each y value. So for my next y value, I start off with y is equal to 3 times 0 minus 1. So giving me y is equal to 3 times 0, 0. 0 minus 1, giving us y equals negative 1. So my next y value is going to be negative 1. Next, I substitute 1 in for x, showing my work again. Y is equal to 3 times 1 is 3. Bring down the minus 1, so I get y equals 2. My next y value, therefore, is 2. And my final x value is 2, so I substitute that in. Y is equal to 3 times 2 minus 1, so I get y is equal to 3 times 2 is 6. Bring down the minus 1, and I get y equals 5. And that is it. That is all the work that I would need to show to fill in my table for y values, for x values negative 1, 0, 1, and 2. I get y values of negative 4, negative 1, 2, and 5. And so those 4 ordered pairs represent the equation y equals 3x minus 1. Alright, I know we're getting a little pressed for time, but we still have a few things that we need to go through, so bear with me. Our next example, we have y is equal to 1/2 x plus 3. Again, one negative x value, I would use 0, and then a couple positives as well. So our 0, I would encourage you to probably always put that there in that particular row. Now, when it comes to filling out the rest of our x values, we could choose negative 1. We could put negative 1 here, 0, 1, and 2, just like we did for the previous example. However, that's going to make this calculation, this math here, a little bit more tricky and a little bit more complicated. Instead, what I would encourage you to do is use multiples of 2 from this value here. So go up by 2's over here, down by 2's over here. So going down by 2's, we would have negative 2 in this spot, positive 2 here, and then 4. Using these values for x is going to make our math up here much simpler. So same steps as before, copy down our equation. And then I'm going to substitute each of these x values one at a time in for x here. So first, I'm substituting negative 2 in for x. So I have y is equal to half of negative 2 is going to give me negative 1 and bring down the plus 3. Negative 1 plus 3 gives us positive 2. So our first y value is going to be 2. Next we move on to substituting in 0 for x. All right, so I substitute in 0. Have y equals half of 0, half of nothing is going to be nothing, or 0, and bring down the plus 3. So I get y is equal to 0 plus 3 is 3. Next I'm going to substitute in 2 for x, and so I get y is equal to half. 1/2 times 2 plus 3, well, half of 2, if you have $2 and somebody takes away half your money, you're left with $1 plus 3, bring down the plus 3, so I have y is equal to 4, so that's my third y value. And lastly, I substitute in 4 for x, so I have y is equal to half times 4, 1/2 of 4 is going to be 2, and bring down the plus 3, so we get y equals 5. Alright, and that completes our second table. So when it just comes to filling in a table like that, all we need to do is choose our x values according to whatever we think would be easiest x values to substitute in. And it's basically substitute and evaluate. Substitute the x values, evaluate the equation to get our y values. Now, it is my hope that you guys recognize that we have a pattern here in our x values where we're going up by 2's, and as the x go up by 2's, the y values go up by 1's. If we see a pattern in our x values, we should see a pattern in our y values as well, if we've done the math correctly. Alright, now there is one more example I want to do. It's more of a real-life example. And before we get to the last example, I have one more little set of notes that I want you to copy down. Alright, and so here's the note. When making a table for a real-world situation, choose values for x that make sense in the context of the problem. For example, let's say you're given a problem related to shoveling driveways. You're not going to choose an x value that has negative x values that are negative, because you're not going to be able to shovel negative driveways. Going to somebody's yard and shoveling snow from the yard back into the driveway does not count as shoveling negative driveways. Also, we're not going to choose a huge number either, because unless you've got an army of 8th graders out there shoveling driveway, you're not going to shovel thousands of driveways in the course of a single day. So choose values for x that make sense in the context of the problem. Alright, so our last problem, example 5, says the equation y equals 2x plus 5 gives the total height y of a plant that was 5 centimeters tall when transplanted and grew 2 centimeters each day. Make a table of values for this situation. Okay, so again, we go back to our table, and we need to ask ourselves, what values for x make sense in this situation? We're not going to use negative values for x because we can't go negative days into the past. Okay, that's not going to work. So we're not going to use negative values. We also don't want to use very large values in this situation because we're not worried about the height of the plant 5,000 days from now. We're worried about the height of the plant over the next few days. So what I would encourage you to do for this example, use small values close to 0. Positive small values close to 0. So keep it simple. Keep it easy on yourself. Let's just use 1, 2, 3, and 4. So what we're going to do, we're going to use our equation, use these values for x to find our values for y. I'm going to rewrite my equation here. and I'm going to take each value for x, substitute it into the equation. So we start with y is equal to 2 times 1 plus 5. I took my first x value here, substitute in for x here. So now I have y is equal to 2 times 1 is 2, plus 5, giving me y equals 7. So after 1 day, the plant has a height of 7 centimeters. Next I'm going to substitute 2 in for x. Alright, I've substituted 2 in for x. Now I have y is equal to 2 times 2 is 4. Bring down the plus 5. Y equals 4 plus 5, so y equals 9. My second y value is going to be 9. So after 2 days of growth, the plant is 9 centimeters tall. Next I'm going to substitute in 3. Solve this for substituting in 3 for x, and I get y is equal to 2 times 3 is 6, plus 5, and get y equals 11. So after 3 days growth, the plant is 11 centimeters tall. Finally, I'm going to substitute 4 in for x to find out how tall the plant is after 4 days. Now, I do want you to show this work, but as I said earlier, we should see patterns. We have a pattern in the top row, so we should have a pattern in the bottom row as well. So we should be able to look at the pattern for the y values and determine what this y value will be even without doing the math. However, I do need to see the math for now. Alright, so finally, substituting 4 in for x, we have y is equal to 2 times 4 is 8, 8 plus 5 gives us y equals 13. So after 4 days of growth, the plant is 13 centimeters tall. Alright, so again, this lesson has just been about finding and filling out tables for representing non-proportional but linear relationships. And so if you have any questions, write those down and we'll talk about those in class on Thursday.